Hello everyone. Our topic for today is analysis of trust. But instead of using our conventional way of using the joint method and the section method, we're going to use another method that we can solve all of the members' internal forces using the matrix method. Actually, there's a limit of using this method, same with the other conventional way, because it only uses if the equation that we're computed during the analysis is can be solved using system of linear equation. Okay, but to show you how to solve this, so let's have an example. Same with the figure at the right side of your screen. So here's the truss with one, two, three, four, and five members loaded 50 kilonewton at point B for going to the right. So let's analyze this truss to solve all of its internal members and also its reaction to the support. So here is the way how we computed them. Okay, so actually, the process that we're going to use is this from the joint method. But what we're going to do is we're not going to solve the reaction. Meaning, we will remain it as an unknown so that we're going to solve them simultaneously with the other internal members. So first is what we're going to do in matrix method is we're going to analyze each joint, all of the joints by using the summation of forces vertical and the summation of forces horizontal. So we will start with point A and then we will end at point D. So as you can see here, we have the assumed reaction AX, AY, and then CY. Let's start with joint A. So using summation of forces horizontal equal to 0. So all of the forces going to the right is equivalent to the forces going to the left. So let's draw first joint A and all of the members that are connected at point A. This is your joint A. This is AB. First, we are going to assume that all of the internal members is in tension. AB, and we have here your AX, and then going up AY. AB has a slope of 3 and then 4. So therefore, its hypotenuse is 5. So therefore, we can solve now the equation for forces that are acting horizontally. So we have AX plus AB that is or plus or no, plus AB times 4 over 5. Since we don't have forces going to the left, so therefore we equate this equation into 0. So this equation will be considered as our first equation. Next, using the summation of forces vertical equal to 0, all of the forces going up must be equal to going down. So vertical forces that are going up is AY, then plus AB multiplied by 3 over 5. Since we don't have forces going down, so that is equivalent to 0. So this is our equation number. Okay, next, let's analyze joint B. So in joint B, we have these forces, internal member. We have here AB. We have also BD. And we have BC. And aside from that, we have the external force applied at point B with a magnitude of 50 kilonewton. So the slope of two horizontal or two diagonal internal members are 4, 3, and then 5. 4, 3, and 5. Okay, so let's analyze uh, the forces. So using summation of forces horizontal equivalent to 0, all of the forces going to the right equals to going to the left. We have 50 kilonewton plus BC times 4 over 5. Then that is equivalent to AB times 4 over 5. So let's rearrange all of the terms in this equation so we have uh, correct format for a system of linear equation. So we have AB 4 over 5 minus BC 4 over 5. Then that is equivalent to 50 kilonewton. So that is our equation number. Summation of forces vertical equal to 0 for joint B, going up, going down. So as you can see, we don't have forces going up. So all of the forces are going down. We have 0 is equivalent to AB times 3 over 5, and then plus BD, then plus BC times 3 over 5. So rearranging in format of linear equation. So AB 3 over 5 plus BD plus BC 3 over 5. So we have equivalent to 0. So this is your equation number 4. Okay, next, we're analyzing now joint C. So in joint C, here is the internal forces and then other reactions that are connected at joint C. So we have BC, and this one is CD with the slope for BC, that is 4, 3, and then 5. And then a vertical reaction at joint C. So this is your CY. The summation of forces horizontal must be equivalent to 0, going right, also going to left. We don't have forces going to the right, so that's equivalent to 0. Then, going to the left, we have CD plus BC times 4 over 5. Rearranging, so we have BC 4 over 5, and then plus CD is equivalent to 0. Equation number 5. Then, summation of forces vertical, 0. Going up, also going down. The force going up is CY, and plus BC times 3 over 5. Then that's equivalent to 0. This is our equation number 6. Then lastly, analyzing joint D. So here's the internal members connected at joint D. We have BD. We have also ED and CD. There's no external forces or reactions connected at joint D, so you can compute now. The equation using summation of forces horizontal equal to 0. Going to the right equals to going to the left. So we have CD is equivalent to AD. Rearranging, so we have AD minus CD is equivalent to 0. So this is our equation number 7. Then lastly, summation of forces vertical equal to 0, going up, going down. So there's only one forces that going in the direction of going up. So we have DD, and we don't have force going down. So that's equivalent to 0. So this is our equation number 8. So as you can see, we have um, 1, 2, 3, 4, 5, 6, 7, 8 unknowns. So if we have eight unknowns, so we need eight equations. So as you can see, we created an eight equation. So this eight equation can be used to solve all of the unknowns using the matrix method. So first is let's rearrange them. Let's rearrange all of the coefficients of the equation that we formed into a matrix form. Okay, here's a summary of all of the equations that we formulated from getting the summation of forces horizontal and vertical on each joint. So here's the eighth equation, and we're going to create the matrix of this eighth equation. First is let's write the coefficient matrix. So we have an 8 by 8 matrix. So we need to identify first what would be the arrangement of our variable. So in this case, what we're going to do is we'll start with all of the reactions, then followed by all of the members of your class. AB, and we have AD. We have also BC and BD, and then lastly we have CD. So first equation, coefficient for AX is 1.0. For AY is 0. CY is 0. AB is 4 over 5. AD is 1. BC is 0, and then 0 and 0. For the second equation, so we have 0 for AX, 1 for AY, 0 for CY, AB is 0 over 5. Then the rest are all zeros. Okay, for equation number 3, AB is 4 over 5. BC is negative 4 over 5. Then the rest are zeros. Next, fourth equation for AB, that is 3 over 5. BD is 1. And then for BC is 3 over 5. And of course, no, the rest are zeros. Okay, next, fifth equation, BC is 4 over 5. Then CD is 1.0. And the rest are all zeros. Next, sixth equation, CY, 1. BC is 3 over 5. 0, 0, 0, 0. Okay, then seventh equation, we have AD, 1.0. CD is negative 1.0. Then all are zeros. Then lastly, for BD, 1.0. Okay, so after this, then we will create the vector of the answer of each these equations that we form. So in this case, so this is your constant vector. So we will just put all of the answer on each on each linear equation. So first equation we have 0. For second equation is 0. Third equation is 15. Fourth, 0. And I think the rest of all the equations are all zeros. Okay, so once we have this equation or these matrices, then we can solve them using the matrix. So how are we going to solve these internal members and then the reaction? So using the linear algebra about using the matrix in the form of AX is equivalent to B. So we know that to solve all of the variables included in the matrix X, this is by the use of the inverse of A, then multiply the matrix B or the constant vector. This is your constant vector, matrix B. And earlier, this is your matrix A. So getting the inverse of this matrix and then multiply to the matrix B here, then we can solve now all of the internal members. So here is the matrix that we formed using those equation. So you can check it, uh, the values. If it is correct, it is the same with the matrix that we formed. So in this case, all of the fraction part is converted into decimal. And we have here matrix A and then matrix B. Then to solve it, we can use uh, the computation of MATLAB using x equivalent to inverse of A, will multiply by. So we'll just press enter, and then here is the answer. Here is the summary of the values from the MATLAB. So take note again of the arrangement of the variables that are indicated in this matrix. We'll start with AX, AY, CY, AB, AD, BC, and CD. So this arrangement will be adopted also in this value. So we have here your AX, this is your AY, this is your CY, we have your AB, AD, you have your BC, and BD, and lastly CP. So negative sign indicates that it is on reverse direction. For reaction, we assume that AX is going to the right, so the correct direction is going to the left. For AY, so it is negative, so therefore the reaction is going down. For CY, it's positive, so that's correct direction, going up. For AB, this is under tension. So we assume that all of the internal members have a tension force or tension internal force. Therefore, AB is in correct direction or has a positive value, so that's under tension. For AED, this is under tension. We see a negative value, so that is compression. For BD, zero, so of course, no, it's either under tension or compression, but it doesn't have any internal force. Then for CD, this is under tension. So therefore, this is now the final answer of internal forces and then the reaction for your Truss system. And that's how we solve our Truss on its internal members. So, what do you think? It is easy or it is a very long method? But it's up to you how to design, how to analyze your trust. Any method will do, no, as long as it's convenient for you. But I think this method is not applicable for written exam since it involves a large matrix, so we cannot solve them manually. It's very hard for us to solve them. So if we are implementing such technology such as using MATLAB, or you can use also Excel to solve this, then it's much faster compared with the other methods. Okay, so that's it. Thank you for listening.